All right, so now we're at of the part three of the examples of applying kernels, like kernelizing a linear algorithm. And in part three of the example, we're going to go over kernel ridge regression. Okay? So this assumes that you already know ridge regression really well. If you don't know ridge regression, make sure you review that. We are not going to assume we're not going to go over what ridge regression is. Um, the the equation for ridge regression is here, and it's mostly featured by the addition of this term into into a linear regression or just regular regression. All right, so just like all the other examples, here we have an objective that is basically in terms of summation. If we want to convert this into kernel formulation, like kernelizing this objective, most of the time it's easiest. It's much, much easier if you simply convert this into the matrix format first. So let's do that first. Okay. So over here, we have the square. Let's just look at the square term here. And square of this is just this multiplied by this. Now we can expand the terms, right? So if we expand the terms, your this times this will end up with this. The cross terms are equivalent, so you have two of them. And then y over here. So basically, this summation is divided into three separate summations. Now, if we look at this summation closely, well, this summation, what is this? It's basically W and W on both sides, and then it's summing up all of the vectors. So x times x1 transpose, x2 times x2 transpose, so on and so forth. So this summation is really summing up all the x values. Now, in a previous lecture, we have gone over how you can divide multiplications of vectors, right, into dot products. So notice how if you put the dot product down, so we are treating vectors here. We're treating vectors as if they're numbers. So we can this is what we went through in a previous lecture, that you are able to just split. So notice x1 transpose. If you multiply this dot product down, you're going to get the same thing. Which means this is just equivalent to this. Now, this right here is the standard X matrix that we've done many, many times, and this is the X transpose. So, in short, this entire thing can be written as this in terms of the matrix conversion, like it converted from summation to matrix multiplication. Similarly, we can do this with this one, right? So this is this over here is the second term. So in the second term, LB, well, 2W. So W doesn't change and 2 doesn't change. So we can pull those out. The things that change is y1 times x1, y2 times x2. Now, y here, the y values are the labels, and therefore they're scalar. They're just numbers. However, the x values here are vectors. And this implies that you can now pull y out and the x out as well. Notice how, once again, when we multiply this down, this works so that they're actually equivalent. Now, this right here is the x transpose, just like the previous example. And this is the y vector, the label. So x transpose on y. Therefore, we can convert this also into a format where it's matrix vector multiplication. And notice how this is much easier to implement than if you had to do a sum, right? And this is also very easy. So this is just equal to y1, y2. Actually, it's a summation of these. So you can then pull the y1s out. So notice y1 times y1, y2 times y2, y1 times y1, y2 times y2. And once you pull this out, you see that this is just y transpose y. So this is a vector multiplication. So we've converted essentially all the sums into vector multiplication. right, with these terms here, right? So this is converted into this is converted into this, and this is converted into this. And lastly, we have this term here. This term, well, this is just, remember, the W norm is equal to, let's say W is two dimensions, right? W1, W2. So let's say it has two dimensions. Therefore, the norm, L2 norm, is the square root of W1 squared plus W2 squared. Now, if you square that, then this disappears, right? And this right here is equivalent to W1, W2 times W1, W2, right? So this is just W transpose W. So what I'm saying here is this can also be transformed into a matrix, a vector multiplication. So this is how we got W transpose W here. Okay, so in any case, the idea is we have a bunch of summations, and we converted the summation into matrix vector or vector multiplication. Once we have done this, we're going to follow the patterns that we have done throughout the last several examples with PCA and LDA. We simply convert the data X matrix into the phi. Okay, so this right here, the X matrix, when we convert into phi, instead of X transpose X becomes phi transpose phi. So every location there's X, we just convert that, and that's it. This is how you convert a linear model into a nonlinear model in RHS. So once we kernelize this, right, the next thing we have to do is basically solve for W. And there's a closed form solution, so we can simply take the derivative of this and set it to 0. Now, this right here, we can view that as just a single matrix. This is a quadratic. So this is a quadratic. This is a linear, right? We're finding y times phi transpose. Imagine that as just a vector. So that's like a vector. So this is a linear. Therefore, when we take the derivative, the quadratic becomes 2 phi transpose phi, right? And then the linear, where's the linear? The linear phi, so the W goes away, right? So it's just this left over. And then when you take the derivative of these, there's no W, so they cancel out. Oh, wait, there's a W here. So the W here is just 2W. Okay? 2 lambda W. Yeah, here we go. Okay, so if we set this is the derivative, and we set the derivative to 0, after you set the derivative to 0, let's see, set the derivative to 0, we can pull the 2 out, so the 2 is the same, and the W out, so the W out. So therefore, this right here, 2 phi and lambda I can be combined together to form this, and then minus 2 phi transpose t. And now I move this to the other side. Therefore, this is equal to this here. Okay. Now, the 2 cancels out. Okay, that simplifies things. So we cancel out the 2, and then we simply find the inverse of this. So W is equal to the inverse of this matrix here. You see the inverse? So this is it. This is the closed form solution for W. However, there's a minor problem because phi could potentially be a matrix of n by infinity. Therefore, phi transpose phi would be potentially a matrix of infinity by infinity. So this is a standard problem we run into in kernelizing the method that we often run into dealing with phi. So the key here is we don't want to deal with phi. We want to deal with kernels. So how do we go about converting them into the kernel matrix? Okay, like note, the kernel is phi transpose, but we have the opposite, phi transpose phi, right? So the dimensions are not the same. Okay, so what should we do in this case? Well, it turns out there's a very old inverse property that was already proven, and we can just rely on this property. The property is if you have some matrix, the inverse, times something, inverse, times something is equivalent to this. So this property looks kind of crazy, but it turns out to be really useful. If we let P, this one, equals to lambda I, R inverse equals to I, identity, and phi equals to B, then we can rewrite our equation into the same form. Notice you have right here, this is P inverse, and then B transpose RB. Right? Notice how we can, this is identical to this form, and then B transpose R right here. So if that's the case, this right here must equal to this. And then notice how I converted this over here. So PB, what was P? Is basically lambda. So the inverse of that will be 1 over lambda. And then B transpose is just phi transpose. So notice PB, I color coded them, and the red portion is the same, and then the black portion is the same. So we can essentially convert whatever we had into a new form. Now the advantage of this conversion, is that once we convert this, we can further simplify it. Notice how this is inverse of lambda. So it's inverse of lambda. When you have inverse and inverse, you can combine them. So this moves inside. So now it's lambda times lambda and lambda times the identity. Notice how this is moved here and here. So, okay. So this cancels out, implying that what we have is phi. This is a kernel because it's phi transpose, and that's it. So this now is our solution, W star. Now remember, W star in the kernel sense, we can view it as a function. So this is the function essentially of what we want, right? Now that we have the function, we use the reproducing property. If we want to evaluate this function, then we plug the x in, then it's our whatever our function is, which is here, multiply the feature map version of x, right? So if you want to know what this value becomes from this function, you first plug it into the feature map and take it the inner product with the best function we found. And I just told you this function is equivalent to this. So I'm going to copy it down. So this is copied down. Once I copy this, now imagine, you can kind of picture this way. This is this here. This right here, you can picture as just the alpha. So this right here is the perfect function that you have. Okay? So it's always in the same form that we talked about. Now, what is phi? Well, this is just phi transpose, but capital Phi transpose is equivalent to the vectors of each one of them. And then this is a kernel, so it's equal to a kernel. The rest is the same. Now, let's leave this alone for now. Just look at this. If we actually multiply them together, then you're going to have the inner product of x phi x1, right? And this is the definition of x1. Okay? So therefore it's just a kernel value if you plug x in and x1 in. So if you're trying to evaluate particular x, right, you need to plug it in while using the first sample, second sample, so on and so forth. So this right here, if you want to evaluate x, this right here is essentially the equation. You plug x into each one of these and then multiply by this result. Okay. Now, I'm going to denote this vector here as kx because we're plugging x in. And that's it. This is equal to this expression. Okay. All right. Now, if we're like, this is when we're evaluating single point. But what if we want to evaluate the entire data set? Right. So this was what we just did. Same thing here. Okay. Now, instead of x, we want to evaluate the entire entire data set, the capital X. Well, in that case, instead of just f times one of them, then it's going to be f times multiple of them, right? So you're going to evaluate for sample one, sample two, sample n. And this, we once again plug f in. So here is the f, color coded in red. Now notice this is the definition of a kernel, so that's a k. This is also definition of a kernel, k. So if you want to find so once you know the alpha values, right? Once you know the alpha values or the f star, once you know f star, well, to evaluate the prediction for every single sample is simply the kernel matrix times kernel matrix plus lambda identity inverse times y. So this right here is how you go about getting the values for every single sample. Okay. All right. So over here, I wrote the code for ridge regression. Notice how I wrote here k and then k plus lambda I inverse y right here, this line. So this then allows us to make prediction on every single data. So over here, I show you the prediction versus the truth. And you can see that it does a pretty good job making the prediction, where the prediction and the truth are really close to each other. Okay, so this right here is the code for kernel ridge regression. Okay, and let's see. Yeah, so for practice today, I would like you to load this file here and see if you can essentially write your own. So once you load this, ideally I want you to basically find P of X. So this right here is the data, this data set, and I want you to find the probability distribution of P of X for this data. Once you find this, using KDE, I want you to essentially use kernel regression and kernel ridge regression to find p hat of x such that they're approximately the same. Okay, so if you know how to use KDE to essentially find p of x, you can predict the probability, right? And therefore you can train a separate function to approximate the original one, and you can essentially use kernel regression for this. Okay, good luck doing this. This will be a really good training for you. All right, I will see you in the next lecture.